ask their supervisor to come. So first, Klaus Hansen.
Thank you, Lydia. Also, thank you very much, Andreas, I think in the name of the community, for moving all of this forward, and in particular, this quantum center. But now let's move into science. And the first talk will be given by Chuyao Tong, and she will talk about spin and valley blockade in graphene. Please, Chuyao.
So hello everybody. Thank you very much for coming. My name is Chuyao Tong, and I'm a PhD student in Professor Ensing's group. And today I'm very excited to talk to you about our exciting bilayer graphene quantum dot system that we're working on, and a little bit more specifically about the observation of Pauli valley blockade and spin blockade. So I'd like to start with a little motivation of spin qubits. To make a qubit, we need a two-level quantum system. And for example, we can have the easiest thing to do with a spin is that you can encode a 0 with a spin down state and the 1 with a spin up state. Now, if these states decohere, then they interact with the environment, they lost their states, then the information is also lost. And this decoherence can come from, for example, some magnetic noise. And this can majorly come from, let's say, the hyperfine interaction with the sea of nuclear spins surrounding our spin state, and also the spin orbit coupling. And this is where graphene comes in, because graphene has naturally 99% of carbon-12, which is spinless. So that solves the hyperfine interaction. And it also has a low atomic mass, which gives it low spin orbit coupling. Therefore, graphene has been long predicted to be a quantum dot system where it can have long spin coherence time. And hence, we're looking into the holy grail of graphene spin qubit. Now, to be able to make a spin qubit, to be able to have these spin states, we also need to single out these electrons or holes, these charge states with the spins, to single them out from this sea of spins. And therefore, we need to confine the charges in a quantum dot. So quantum dot essentially is a zero-dimensional thing. It's a zero-dimensional charge confinement. It confines the charge in this pinpoint of space where it can't go anywhere but can only stay in this one point. It has also discrete energy levels. So we need to start, we have a three-dimensional space, so we need to start with this, and we need to, in the end, reach a zero-dimensional point. To go to two-dimension, that's easy, because we're working with graphene, and graphene naturally is a two-dimensional material. But how do we make it one-dimensional, even zero-dimensional? To be able to do that, we need a controllable, ideally controllable energy gap. Let's take a look at the energy gap in graphene, the band structure in graphene. If we have a monolayer of graphene, this is just a sheet of hexagonal lattice. We have the band structure here in the y-axis is the energy, and the plane is the momentum space. We have a direct cone, so the conduction band and the valence band touches at a single point, and there is no gap. Now, what happens if we take another layer? We look at bilayer graphene. We take another layer of hexagonal sheet, and we have two touching parabola of the conduction and valence band. The band structure has changed a little bit, but it doesn't really help because we haven't had a gap yet. What we can actually do is to apply an electric field perpendicular to the sheet of bilayer graphene, and then we open up a gap at the touching parabola. And this gap can be of the size of 10 to 100 millielectron volts. So there we have a gap, and we can start doing our confinement. With a controllable electric field, if we have a sample with a controllable electric field, then we can also control the distribution of the gap, or we can control how we confine our charges. So to do this, I'll show you a little bit our sample geometry, how we fabricate our samples. We first start with exfoliation, like any 2D materials. We take our Scotch tape and we do this, and we put it onto a chip. Then we do the stacking. So essentially, that is us coming with a plastic stamp, what we call a stamp, and to look into the chip and pick up the flake that we want, and pick up the next one, and so on and so forth. To be able to protect our bilayer graphene a little bit, we encapsulate it in 2 layers of hexagonal boron nitride for protection, and also they are working as insulators. So we come in with our plastic stamp, we pick up the first layer of top hexagonal boron nitride, we pick up our bilayer graphene, and we pick up the bottom HBN. In the end, we also pick up a sheet of graphite as a global backgate. It's a good conductor, and it's homogeneous backgate. In the end, we deposit the whole thing on the chip and remove the plastic. We then also need to contact our bilayer graphene. So we add through the top hexagonal boron nitride, and we deposit metal as our source and drain contact. Now, with such a stack, we can start depositing top gates to do some confinement. We first can form a conducting one-dimensional channel. So we deposit two purple gates over there, what we call split gates. And now, together with this global backgate made of graphite, we can tune two things. So if you look at the energy structure again of bilayer graphene, we can tune the gap size, because the gap size is dependent on the strength of the electric field. And that is essentially dependent on the voltage difference applied between the top and the bottom gates. We can also tune where the Fermi energy lies. That is essentially, with the capacitance model, you repel or attract charges in the bilayer graphene sheet. So we can move it up and down such that the Fermi energy cuts at different locations of the band. So for example, we can first apply some voltage in the global backgate such that we have a electron-type conduction. And then underneath these purple split gates, we can have the Fermi energy lying in the gap, and we have a gap opened. Therefore, what we'll have is such a one-dimensional channel where these white regions are gapped, and they correspond to the regions underneath these purple gates. And in the middle, we still have N-type, we still have electron carriers, so we have a one-dimensional N-type electron conduction channel. So there we go from 2D to one dimension. And now with a quantum dot, we can also deposit a second layer of gates on top. So we first deposit an insulator aluminum oxide to separate the layer of the second metal layer with the first metal layer. And on top of that, we deposit our second layer. Again, like before, we have N-type region. We can also make gapped region. And if we want to make these two regions gapped, no, it's fine. I think it's my computer. Sorry. If one can make these two regions gapped, and then we essentially block the transport, so these two regions are gapped, and we now have a N-type island isolated in the one-dimensional channel. So now we have an electron dot in the N-type channel. So we go from 1 dimension to 0 dimension. We block another dimension. And of course, we can also use this green gate in the middle. By applying more and more voltage, we can change this region in the middle, from N-type to gapped to eventually P-type, such that the Fermi energy cuts in the valence bands. We have holes. So then we can revert this region, and we can have a P-type. We can also have a hole dot in a N-type channel. Now, to come back a bit on the spin qubit motivation, to be able to make a spin qubit, we also need to be able to read out our spin states. And now, this is notoriously hard to do because spins are tiny, tiny, tiny magnets, and it's really hard to do that. But actually, what we're really good at is we're really good at reading out of charges. That has been refined for over years, and that we can do. So now, ideally, we would like to be able to have a way to convert the spin states to a charge state, such that we can, instead of reading spin states, we can read the charge states. And that can be realized by an effect called Pauli spin blockade. To be able to see the Pauli spin blockade, we need a double dot system. So here is the same sample that I was showing you before, but now instead of having 3 of the second layer gates, we have 5 gates. 5 gates, we can form a double dot system. So this is what the band structure will look like. Underneath these 3 green gates, these are the barrier gates. We can have Fermi energy cutting into the gap. And underneath these 2 yellow gates, they are the plunger gates of the quantum dot. There we have 2 puddles of charges two part of regions the charges can go in. So now we use these 3 gates because the Fermi energy is in the gap. They form the tunnel barrier. And then with these 2 yellow gates, we can tune the energy levels in the quantum dot. We can tune them up and down and up. And with a quantum dot, we can have discrete number of charges in such a dot. So here I show in the x and y axis is the voltage that we can apply to these 2 yellow gates, to the plunger gate. And in the middle, we have a discrete number of charges And we have higher energy levels that we need to reach to be able to load a more number of charges onto the dot, and then lower energy levels that with less number of charges. So we can label these regions with the charge carrier numbers. And to be able to have transport, we need to have the electrochemical potential in the source to be equal to the energy level to here to NL plus 1. That is equivalent to such a line in this plot. And to be able to have conduction on the other side, to be able to go into the drain, we also need that, the energy level in the right to align with the drain, and that's equivalent to this line. And we also need 2 energy levels in the middle to align with each other, and that is such a line. And in the end, only when these 3 lines meet with each other, when all of the energy levels align, we can have transport and we can have current. So at only this one black dot point, this is where we can have current. And we can have an electron happily going through all the levels. And now we can apply a bias voltage, such that now we have a window of region that we can do. Because not only we can have electron transport when the energy levels align, we can also have electron transport when there's a little bit misalignment, so long as it drops a bit of energy each time. So essentially, we increase these lines into a region of conductance. And then this region, this width of the lines is defined by the size of the bias we apply. And at the crossing point of these 3 lines, we have a region of area where we can have conductance, we can have current, and that is called a bias triangle, finite bias triangle. So now let's look at how we actually have Pauli spin blockade. For a conventional Pauli spin blockade to start with, we have already 1 electron sitting in the left dot, let's say, for example. And let's say this electron has a spin of spin down. And the right dot, we leave it empty. Now, we can have electron transport from left to right. Let's say we want to load in a spin down electron from left to right, from the source to the left dot. It cannot really go there because the Pauli's exclusion principle says that we can't have 2 electrons with the same quantum numbers. We already have 1 spin down, we can't have another one. And therefore, this electron needs to go to a higher orbital state. But that needs energy, and it does not have enough energy to do so. Therefore, we concluded that the spin-down electron cannot be loaded into the left dot in this scenario. However, let's consider when we have a spin-up. This guy can go on to the left dot with no problem because we can have now anti-parallel spin alignment. And it goes on to the right dot, no problem, and then it leaves. So therefore, we have transport and we have conductance. So with a spin-up, if we load in a spin-up electron, we can have transport, we can have current. And since the source is essentially an infinite reservoir of spin-up electrons, you can always continue this process. You always have electron transport and you always have current. But now let's look at the situation when we go from right to left. Let's first look at the spin-up electron. Again, it has no problem entering the right dot since it's empty, no problem going to the left dot since it's anti-parallel, and no problem leaving. And with a spin-up electron, we can have transport. However, the situation is different now if we load in a spin-down electron. Now, it has no problem going into the right dot because the right dot is empty. But now it can't really go on to the left dot because it has to go to the higher energy state and does not have that energy. And the problem is that it can't go back either. It can't go back to the drain because it already lost its energy. It doesn't have the energy to do that either. So this electron is essentially stuck in the right dot. And what's worse, it causes a traffic jam because you can't load another electron onto the right dot anymore since that level is occupied. Therefore, the moment we have a spin-down electron loaded into the right dot, the electron transport is terminated, and we have no current anymore from this point onwards. And this effect is called the Pauli spin blockade. Now, to be able to utilize this, as I promised before, to do a spin-to-charge conversion, we can put a nearby charge detector, for example, another quantum dot capacitively coupled to this double dot system or a quantum point contact, such that it essentially sees the movement of charges as a discrete steps of signals. We can have a detection signal, and in the y-axis we plot the signal of the detector, and the x-axis we plot time. So first, we consider the electron in the right, in the drain. Nothing happens until it gets loaded into the right dot, and we have a step in the detection signal, we see this movement. And then nothing happens because it's like to stay in the right dot for some time, until the spin up can go into the left dot, but the spin down cannot, because it's stuck in the right dot. And then the spin up spends some time in the left dot, and then eventually it leaves the left dot, and this is detected, whereas the detection signal in the bottom case for the spin down electron has never changed. It always stays the same because it never moved. And with this, we can use these two different traces to check which spin we have, which spin of the electron we have, whether we have a spin up or we have a spin down, because the behavior is different. So with that, we formed a conversion from a spin state to a charge state. Now, that was traditional spin blockade. But with graphene, life is a little bit more difficult because we have an extra valley degree of freedom. So let's come back to graphene's band structure. We have this parabola with the gap open in the middle. But with this, because of its honeycomb lattice, graphene has 2 atoms per unit cell, which gives it 2 non-equivalent points in the momentum space that looks like this. So we have 2 points that looks like this. And these values also act as a quantum number. So in the end, we have 4 times degeneracy, not only up and down as spins, and also values k minus and k plus. We have the combinations of values and spins as the 4 times degeneracy. Now, this makes life a bit difficult, because if we look at the 2-electron states on a single dot, we can have orbital degree of freedom and spin degrees of freedom. With the orbital, we can have an orbital symmetric wave function or anti-symmetric wave functions. With spin, we know that we can have a triplet arrangement of 2 spins, which is 3 times degenerate, and we can also have a singlet, which is 1 time degenerate and is anti-symmetric. Now, because electrons are fermions, so overall we need an anti-symmetric wave function, so we need to combine the symmetric with the asymmetric and asymmetric with symmetric. We have 4 states. We can have asymmetric orbital wave functions with a spin singlet, and then we can also have anti-symmetric orbital wave functions with the spin triplet. And these 2 energies, wave functions are separated by exchange energy. And that exchange energy is very large because essentially it's related to the energy difference between the symmetric ground state orbital wave function and the high energy anti-symmetric wave function. And this is where this is the energy that governed the spin blockade before. This is energy that stopped us to have 2 spin down electrons in the same dot. Now, with graphene, we add an extra valley degree of freedom, and the valleys, because it's k minus, k plus, they can also form triplets and singlets. And to be able to have overall anti-symmetric wave function, we now have 10 times 10 states, which has the anti-symmetric orbital wave function, and 6 states of symmetric wave function. So suddenly the states explode, we go from 4 to 16. Now, luckily, the experiment has tells us that the symmetric orbital wave function, these 6 states are our ground state. And the exact order of these states in energy is determined by short-range interaction, and that is measured in the experiment. So for example, with the 2-particle excited state experiment and also 2-particle Kondo effect, we can see that the ground state of this system is actually a spin triplet and valley singlet. They are 3 times degenerate, and then about 300 to 800 microelectron volts above that, we can have the spin singlet and valley triplet. Now, this changes our Pauli spin blockade a little bit, because now the ground state is a triplet. The triplet means that you can have parallel or anti-parallel spin alignment. It does not care. So now we can have whatever. We can have a spin up coming in, then it will go into a triplet T0 state. It can go out. And we can also have a spin down coming in. You go into a triplet minus, and it also goes out. So the spin blockade does not work anymore because the triplet allows everything. Now, we have no spin blockade, but actually the ground state is a valley singlet, so we can have valley blockade. So what we need to do is just to change the labels a little bit. We change the spin up and downs into valley k minus and k plus, and the exact same thing happens as before. We have a valley k plus when there's already valley k minus in the dot. It can go on because we require a valley singlet. It leaves, no problem. And we have a valley k minus. It comes to right. It goes in, does not go in because we want a singlet, and then it cannot go up either, and it's stuck. So we have a valley blockade. Now, in bilayer graphene dot, we can measure this by the voltage plot that I explained to you a little bit before. So in the x-axis is the voltage on the left plunger gate, the voltage on the left plunger gate, and the y-axis is the voltage on the right plunger gate. And as we said before, we can have a bias triangle with current. And here you can see that everything else is dark. The dark means that there's low current, and then we have a triangular shape when there's current. Now, at the yellow dot is when the energy levels are aligned, just like before. And then going along the blue arrows is when the energy levels are a little bit misaligned. But we can still have transport, we can still have current. Now, in the other direction, if we look at the transport direction from right to left, we can see this Pauli valley blockade by the current being reduced. You can see that the triangle is a lot darker than the triangle on the top. And it's because the electron has a traffic jam as soon as it comes in with the wrong valley. There's no current. And you can see that the current is not completely zero. Maybe it's a bit hard with this beamer, but it actually is not completely zero, but relatively weak. It means that it shows that the valley can actually has a finite lifetime because it stays in as a valley, say K minus or K plus. And at one point, it can perform a valley flip. And then once it flips its valley, it can go on to the next dot again. And therefore, there's a weak current going on there. On the edges, you can see that there's a little bit of current. That is the situation when the energy with the right dot is aligned with the drain potential. And therefore, it can always go back into the drain to change off a valley that is now allowed. And it can continue the transport. And again, before we had the spin to charge conversion, and with valley blockade, we can have the same. We can have the valley to charge conversion. But we still have no spin blockade because our ground state is still a spin triplet. What we can do actually is that it turns out that the spins will split each other in magnetic field in the form of Zeeman splitting. And there's a spin G factor of 2. And now in the valleys, they also split in a Zeeman-like way of splitting with a G factor that is much larger than the spin G factor, 10 to 100. And we can utilize this to create a spin singlet ground state. Before we have zero field, we have no spin singlet ground state, no spin blockade, but now we can just make one. So this is the energy level we have before, and now let's apply some magnetic field. The spin triplet ground state is going to split with a spin G factor of 2, and the valley is going to split with a G factor of much larger, which means that because it's much larger, at one point the valley state is going to be lowered enough energy such that it crosses the spin triplet and becomes the new ground state at this point onwards. Now our new ground state is a spin singlet valley triplet. So with a spin singlet, we can recover our spin blockade again. And this can be seen from the measurement. In the left to right direction, that's the non-blockaded direction, everything is allowed. The bias triangles are high in current. Whereas in the spin blockaded direction, from the right to left, we have an electron traffic jam and we have a Pauli spin blockade. And you can see that from the baseline of the triangle is really dark and the current is suppressed. Now, at one point, you can see that there's a little bit of current starting, and this corresponds to when the electron is stuck to begin with, we shift the energy levels of the spin triplet that is now high in energy down, such that a spin down can tunnel, but still we have a requirement that it has to be a valley singlet at this energy state, so we still have a valley selection, and at that point onwards, on the gray arrow onwards, we have a Pauli valley blockade, which is a lower current, but not as low current as the spin, since valley has a shorter lifetime than the spins. So I hope that I can convince you, that to conclude, I hope that I have convinced you that we have very highly tunable bilayer graphene quantum dots, and we have a good control valley degree of freedom, not like in other systems, such that we can even observe the Pauli spin blockade and the valley blockade, and then we can switch between them using this valley degree of freedom. Therefore, with the observation of Pauli blockade, we can realize spin or valley to charge readout. And if you want to read more about this work, you can go on to my paper on arXiv. And we also have other exciting bilayer graphene dot experiments in our group. We have time-resolved charge detection by Rebecca. And we have tunable valley splitting. We can also go to a higher coupling regime to look at Kondo physics in quantum dot, or we can also perform single-shot Alzheimer readout, and more. So hopefully I've convinced you that graphene dot Valley spin and qubits already on the way. We're really close to getting there, and we have a very fun, exciting graphene quantum dot system. Thank you very much, everybody, for listening to my talk, and I'm happy to have any questions.
Thank you very much, Chuyao. Are there questions, comments? Yes, please.
Just to verify, all of the examples that you gave with the spin down as a starting point, you could have started with the spin up, and then it's always times 2, right?
Yes, it does not matter. Then it's the other spin species that's blocked. So you can always flip the...
But then can you actually decide whether you read out spin down or spin up?
Whether you read out spin down, so whether you load in first spin down or spin up, do you mean?
Right, so I mean, you wanted to use it as a spin readout. But you don't know if the first spin that was...
So what you can actually do is you can split the first spins with a Zeeman splitting, and then you can selectively load in one spin species compared to the other spin species, and then you know exactly which one is already in, and then you can do this onwards.
Yeah, thanks.
Hi, what is your procedure for resetting, for cleaning the system once you're blocked?
Sorry?
Once your system is blocked, and you want to start another, you've done your readout, and do you just put a...
You can raise the energy level of the right dot back such that it's in the drain, such that you can load in a new thing, and then you can reset it. Right? Yeah.
Then again, you need to apply your Zeeman splitting to start a new reading.
You don't need to apply Zeeman splitting to unload the electron that you're already in. You just need to use the gate voltage to lift the energy up to go back.
That I understand, but then when you start a new one, you need to select your spin, don't you?
Yes, if you want to start completely to select the spin already in the dot, then you need to select it in. Yeah. If you want to know what's already in.
Okay, I think in the interest of time, let's thank Chuyao again for her very nice talk.